What I'm going to be talking about is that in the past couple of decades, there have been a lot of major breakthroughs in non-equilibrium statistical physics. One of the actual pioneers of this work, Gavin Crooks, is here in the audience. I'm going to be talking about a small subset of non-equilibrium statistical physics called stochastic thermodynamics. If there's any system that you can think of that's off equilibrium, it's a computer. So not surprisingly, non-equilibrium statistical physics and stochastic thermodynamics in particular has a lot of implication for the ultimate costs of computation, somewhat along the lines of what Fred was talking about the previous talk. So to make things be extremely simple, let's consider a perhaps time-varying master equation that just, if it's going to be, for example, countable classical states, it's just say taking some P0 of x and mapping it through a conditional distribution to a ending distribution. This is applying to any possible physical system that you can think of that can be described by Markovian dynamics along the lines that, for example, Sean Carroll was talking about earlier today. So it could be stochastic dynamics in a genetic network. It could be a digital gate in a circuit. It could be the dynamics of actually the people in this room collectively computing and interacting with one another. If it's Markovian, if we ignore issues of coarse graining and so on, then this is the equation that describes the evolution. And so here's one of the really cool things that comes if you just start from this and nothing more, where you've got an arbitrary time-varying rate matrix. Let's just say, for grins and giggles, we want to calculate the time derivative of this Shannon entropy, and all this can be extended to von Neumann entropy. It turns out, it's about half a page of algebra, that you can decompose it into a sum of two terms. One that people call the entropy flow rate, and one called the entropy production rate. So it's really almost as though entropy is a fluidish kind of thing, that there's some flow with the external universe and there's some intrinsic production, irreversible entropy production. The crucial thing, what's really cool, is that this thing is there, the entropy production rate, the irreversible entropy production, it is non-negative. It doesn't matter what your rate matrix is, it doesn't matter how it varies in time, the time derivative of the Shannon entropy, you're not going to be able to have this go lower than the entropy flow rate. In a certain sense, this is actually a derivation of the second law without worrying about things like Lock-Schmidt paradox or boundary conditions arising just out of the simple equations of continuous time Markov chains. So now let's just integrate this over time, and what we get is this. And this, by the way, is a great review article by Christian Vandenbroek, who recently passed away, in Massimiliano Esposito. You could read this in just a couple of hours. It's a gorgeous article. But what this is saying is that the change in entropy with time, it equals negative the total entropy flow out of the system during your time interval, plus the entropy production, which cannot be negative. So now let's take all of that, which is just mathematics, and start to couple it to real physical systems that are evolving with time. Let's say your system is connected to multiple reservoirs, heat baths, particle reservoirs, work reservoirs, what have you. Because they can all be at different temperatures, KT is not necessarily even defined. Arbitrary number of states, arbitrary initial distribution, arbitrary dynamics, a somewhat technical condition, we assume local detail balance. Then in this particular situation, the entropy flow is temperature normalized heat flow into the reservoirs, okay? This is all coming essentially from first principles. As I say, the math is gorgeous under this. Because the entropy production is non-negative, this means that the entropy flow is actually lower bounded by the drop in the Shannon entropy of your system. The heat flow out of it is lower bounded by the drop in entropy. This is called the generalized Landauer's bound. Notice though, for example, that KT is not even necessarily defined, as well as this has got an arbitrary number of states, arbitrary initial distributions, and so on. To relate this to the more conventional Landauer's bound, to maybe ground things a little bit for people, let's say your system evolves while connected to only a single heat bath. It's only got two possible states. Let's look at the special case where the initial distribution is uniform. Let's say that you implement bit erasure, so your ending distribution is a delta function. In this particular case, the generalized Landauer bound says the total heat flow from the system is greater than or equal to KT log 2. And as Seth just emphasized, when you actually saturate this bound, you are not doing, it's a thermodynamically reversible process. You're not actually dissipating any kind of heat that you cannot actually recover when you actually saturate that bound. You could get it all back, but at the expense of you're now unerasing your bit. Okay, so that's all well and good. That's a bit of a review for people who've not encountered it before with this great work by so many people on non-equilibrium statistical physics and stochastic thermodynamics. But now let's actually push things a little bit. Let's say that you take your system, it could be erasing a bit, could be doing anything whatsoever, and let's say we can saturate all the generalized Landauer's bound so that it is thermodynamically reversible. It's a system that implements this conditional distribution, and it's thermodynamically reversible for some particular initial distribution of its states. That means at the entropy production, when you start with that initial distribution, the irreversible entropy production, the part you cannot recover from the baths, it's 0. But here's something that's a little bit discomforting. Let's take that same system, so it's a thermodynamically reversible system, but run it on a different initial distribution of states. One thing that's not normally emphasized is that thermodynamic reversibility is actually always with respect to an initial distribution. If you run your system that's thermodynamically reversible for initial distribution Q0 on some different distribution, P0, now you are not thermodynamically reversible. And in fact, the total amount of irreversible entropy that you produce is going to be the drop in the KL divergence between your actual distribution and your idealized distribution as the process unfolds. And by the data processing inequality for KL divergence, this is non-negative. So what that means is that if you build any super cool, semi-static, et cetera, device that's thermodynamically reversible for one distribution, because you think that that's the distribution that your device will be run on, but it actually in the real world encounters a different distribution, and it doesn't do something trivial, it's not just a permutation, then it's going to no longer be thermodynamically reversible. Your actual battery is going to drain more quickly. Okay, so to give an example that makes this a little bit pointed, let's go back to Rolf Landauer's brilliant little version of a simple harmonic oscillator, bit erasure. Let's say we're doing bit erasure and we designed our system to be thermodynamically reversible, not for a uniform initial distribution, which is what would give you KT log 2, but instead for something a little bit asymmetric. So I'm running this particular computer here, and let's imagine I've got a whole bunch of, I'm not even sure what they would be, transistors or something even simpler that's just doing bit erasures. And because of the actual dynamics of the computer program, I think that's one particular one is going to have probably epsilon and being in state up and 1 minus epsilon being state down. The minimal entropy flow, the minimal heat generated by this, which is thermodynamically recoverable, goes to 0 as epsilon goes to 0. But now let's say my assumption was wrong, that the system actually is run on a different initial distribution. To make things the extreme, let's say it's run on a delta function distribution. In this case, the total amount of heat that my system produces, the total amount of free energy it takes to run, is minus KT log epsilon. In the limit that epsilon goes to 0, this is infinitely larger than Landauer's bound. So you make your thermodynamically reversible bit. It's thermodynamically reversible for what you think the distribution is. You're wrong in your assumption, and now you can actually violate Landauer's bound to an arbitrarily large degree. Okay? That has lots of implications for computers. Some of them has to do with just straight line, loop-free circuits, like some of the ones that are powering this computer here, and time allowing, I'll get to those. Some of the other ones have to do with Turing machines, everybody's favorite example of a general purpose computational system. There are many different equivalent abstract models of computers, of course. One of the Turing machines, the one I'm going to focus on here, the Church-Turing thesis, or the extended hypothesis, I guess, or the extended version thereof, says that basically anything that we're interested in, loosely speaking, can be done on a Turing machine, any computation that we're interested in. I'm not going to have the time to get into it here, but from my perspective at least, some of the most profound results that humanity has come up with in philosophy actually involve some of the properties of Turing machines, what's sometimes called algorithmic information theory. It's actually gorgeous stuff, and it's very, very deep and profound. But here I'm going to actually look at the properties of Turing machines in a somewhat unusual context, not all that unusual, there was work on this back several decades ago, but somewhat unusual context of their thermodynamics. Let's assume that your Turing machine is given input strings randomly according to what you can view as a coin flipping process. So I've just got a coin, even probability of being up or down. I'm using that coin to set the input string to my computer, my Turing machine, and to make life simple, we'll assume it's what's called technically I should say, a prefix-free universal Turing machine. Then let's say I see an output of the Turing machine and I was uncertain what the input was. Well, if in fact this was the prior probability distribution of generating strings into my Turing machine, then the most probable input, given the output I've seen, is actually the shortest string that causes the Turing machine to compute the output. And this has a name, it's Kolmogorov complexity. Kolmogorov is one of these really obnoxious people who created so much that you can't believe they're actually human. So in addition to like solving one of Hilbert's problems and the foundations of probability theory, he also gave us a lot of the theory of Turing machines, in particular Kolmogorov complexity. The Kolmogorov complexity of some output bit string of your universal Turing machine is the minimum length of an input string that, if you give it to this Turing machine, causes it to compute your output and then halt. Very gorgeous stuff, deep and profound math. But now let's actually try to be a little bit more practical. Say I've, somewhat counterfactually, got a real physical Turing machine, universal prefix-free Turing machine, and what I want to ask is, I want it to produce a particular output, but I don't want to know what's the most compact program, the most compact string I can feed into it to get it to produce the desired output. Instead, I'm very brass tacks. Unlike Paul, I care about my actually energy budget. I'm not a good American, these things matter to me. And so what I want to do is I want to find what is the probability distribution over inputs to this Turing machine that will cause it to compute my desired output and halt. Okay, the prior distribution is Q0 of S. So I'm going to say that if I were to randomly generate inputs according to Q0, which is the coin flipping distribution I'm going to say, then this will be thermodynamically reversible. But if I generate strings according to the coin flipping distribution, my outputs are not all going to be the desired output V. So I'm instead going to generate the input strings according to a different distribution. Therefore, I've got no choice, but I'm going to have some irreversible entropy production. And the question is, after you take all those effects together, what is the minimal amount of entropy flow, the minimal amount of free energy I've got to dump into my Turing machine to get it to compute V and then halt? Modulo some technical details, here's the answer. You can loosely speaking view it as a correction, a thermodynamic correction to Kolmogorov complexity. This thing right here, it's the normalization constant of your coin flipping process in statistical physics, of course. Normalization constants are partition functions, that's why it's a Z. In computer science, it often goes by the symbol omega. It's Chaitin's constant. This is one real number, which arguably includes all of the answers to all of mathematics in it. That's what Greg would say. So an absolutely fascinating beast right here. But for my purposes, it's just a constant. This thing right here, G of IV, that is, given this coin flipping distribution, this is the probability of all possible input strings, the total sum probability, that will actually end up in computing V. So sometimes this is called the Solomonov distribution in algorithmic information theory. And basically, this is now the minimal amount of entropy flow over all possible input distributions, given that they're going to have to differ from the one that your system is optimized for and therefore they're going to actually produce some heat, dissipate heat. The reason for this, intuitively, is that Turing machines, if you think about it, they have all kinds of many-to-one maps. You can start with many different input programs that will all end up producing the same output, and you cannot go backwards from that output to figure out what the unique input distribution was. One of the many lessons that Rolf Landauer taught us is that many-to-one maps are the places that you tend to pay costs thermodynamically. And that's, in fact, intuitively exactly what's driving this extension. Kolmogorov complexity is only the actual single shortest string. Because of all the many-to-one maps, you get these other terms here. So some of the fun properties of thermodynamic Kolmogorov complexity and how it compares to normal Kolmogorov complexity is that normal Kolmogorov complexity is infamously perhaps, unbounded. That if I'm looking at over all possible output strings I want my Turing machine to produce and halt, then the minimal length input needed for it to produce V as I go over all V, that is arbitrarily large. Using one of the many beautiful results in algorithmic information theory called Levin's coding theorem, you can actually prove this kind of weird result that the minimal entropy flow, the thermodynamic Kolmogorov complexity, is actually bounded. So there is a number, you can't compute it, of course, no fun number can be computed, but there is a number such that no matter what output you want to produce, if you were able to compute the optimal input string to your computer to produce that output, the amount of entropy flow that would come out of it, the amount of heat that would come out of it into your heat bath, does not exceed that number. Now, of course, as you can see here, this is like the minimal string to produce V. Remember that we are generating things in the process according to a P of V that only generates our desired output. If I were to randomly sample over all possible input strings, so I'm generating all possible inputs, then it turns out we're back into more conventional kinds of Turing machine theory. The expected entropy flow in this case, where I'm producing all possible outputs by doing coin flipping on the input space, that's actually infinite. Okay, that was just a little bit of a touching on issues having to do with the thermodynamics of Turing machines. It actually gets a lot deeper than that, more challenging might be another way of saying it. Let me now very briefly talk about perhaps the opposite extreme of computational complexity, loosely speaking, which is just straight line, loop-free circuits. Recall that this bit erasing gate, even if it's thermodynamically reversible for some particular initial distribution of its states of the bit, so the entropy production for that distribution is 0, if I run it on a different distribution, then the entropy production is in general non-zero. Now, let's say that like a real computer engineer, the way that I build this computer is I've just got a box full of, well, it's much more than bit erasures, but I got a box full of gates that are all actually, all the ones that do the same thing, all the ones that operate like a physical AND, they're all identical gates. I don't actually try to optimize them ahead of time knowing where they're going to appear in my actual circuit. Well, then the initial distribution of any one of those gates, in fact, will depend on where it occurs in that circuit, because as you go down a digital circuit, whatever your initial distribution of inputs into the circuit was, they get transformed as that distribution gets propagated through the circuit. So the distribution of initial states of your gates is going to vary greatly depending on where it is in the circuit. So therefore, we know that the amount of entropy production generated by this reversible bit erasing gate will depend on its location in the circuit. So I don't have time to get into it all here. I've got very little time left. But this actually has some really deep implications for what optimal circuit design is. You run into NP-hard problems and things along those lines. 1 minute. Let's see if we can sprint. Here's another fun thing that occurs. I'm going to just briefly point to it when you have, when you're worrying about things like straight line circuits. Let me give you 2 bit erasers, both of which are thermodynamically reversible, let's say for a uniform distribution. I run them in parallel. Each one by itself is thermodynamically reversible. Let's say, though, that their initial distributions, even though their marginals were both 1/2, 1/2, there's actual statistical coupling of the initial states of those bit erasers. Now, when I run them in parallel, the overall joint system is not thermodynamically reversible. Running two thermodynamically reversible systems in parallel is not, in general, thermodynamically reversible. That is actually some work that Alec Boyd, who's also in the audience, has done some work related to that, but this also has huge implications for how to actually design circuits so that they have minimal entropy flow. So I'll end it here, pointing people to some resources. There's a wiki. NSF funded us to put this together that's got all kinds of materials from tons of fields related to thermodynamics and computation, a proceedings of a workshop that just came out, and here's a review article that took a lot of my blood, sweat, and tears to put this thing together, but here's a review article that touches on some of it that came out not too long ago in Journal of Physics A. All right, thanks very much.